much for the introduction. So, hello to everybody. As I already introduced, I will present here for basically the CEA List Research Institute, and I will present you the result of this huge project made within the European Processor Initiative project and the Tristan project. Here there are the list of the authors. So, we are talking about floating point computing. Floating point computing means that our data is not fixed inside, like most of you do when you do inference in AI. And we have some bit dedicated for the exponent and some bit dedicated to encode the mantissa within the floating point presentation. Everyone among you is trying to reduce as much as possible the precision during computation. What we try to do is, in fact, extended. In fact, as you can see here, we are trying, we presented this processor supporting up to 512 bits in mantissa and 80 bits in exponent. But why we go that far? When computing in floating point, we have some issues that are rounding and assumption errors. And the additions of these errors may lead to have a large issue, especially not having convergence. This is the classical example that we can have during floating point additions when we want to align the two mantissas. But if we only have, for example, 52 bits of mantissa, once we align the second mantissa for the addition, some bits we are getting ignored or absorbed or cancelled, choose the term that you like. And this is actually one of the errors that we have during floating point computing. And in some applications, especially iterative applications, the additions of this error may lead to have completely inaccurate results. What's the application domain? We are talking about HPC, so far from AI, but still an argument. Basically, in HPC, we want to solve equations, system of equations that we have different type of applications, for example, computational physics, weather prediction, fluid dynamics, and so on. In particular, we focus on linear solvers, which are the basic bricks of these large type of applications, where we have these equations that we discretize in matrices that can be as wide as several hundreds of thousands of elements. Then we iterate within algebraic manipulation, algebraic resolution, trying to solve our linear system. But this iteration may reach also some thousands of iterations. And they mainly take the whole computing time of your doing computation, basically, and there is no guarantee of convergence. And that's where we decided to develop something. Develop something, why? Because this problem is new, and it solves it basically only with software emulation, using software libraries, but that often are too slow for several issues. There are research institutes which wait literally a week before the solver finish to converge. And so we decided to explore a new type of computing paradigm thanks to this core. This core is an extension of the CEA-6 core, call it Ariane if you like it more. And it's an extended precision floating point core. The main thing is that we want to support higher precision floating point data in memory. We get 32 logical, 64 physical registers that supports up to 512-bit mantissas. We get two formats. In the two categories of formats in the goal. The first one in memory, where we can tune it at bit level, the precision, the size of the data, and we support misaligned data in memory as well. And then one internally, where we work in chunks of 64 bits. We introduced a new L1 cache, that L1 data cache that we provided in the Open Hardware group, and we support also a variable precision floating point unit that where their operators has latency that vary depending on the precision of the computer in order to better exploit the trade-off between computing latency, power consumption, and precision. We provide with the Tristan project the XVP float ISA extension. Yes, yet one other extension for the RISC-V community. And the main goal is that we wanted to have a ISA that, in which we can change the precision without recompiling the code. How we did it? We did it basically adding a set of registers, configuration registers that hold the computation precision that our results should have, and we associate it here for which arithmetic, memory operation, and also conversion or comparisons and so on. And that allows us to change the precision, the computing precision at runtime without the need of recompiling the code. We are working also on a compiler, even though we have some issues, and it's a prototype made with a mixed version of LLVM plus Clang, supporting a custom floating point format. What about the variable precision floating point unit? It's a floating point unit supporting the ISA that I showed you before. It supports iterative operations on the floating point mantissa. Why? We cannot have a hardware adder on 512 bits or a hardware multiplier on 512 bits, neither. So we iterate on chunks of 64, 128, 512 bits, depending on the type of the integer operation that we want to do in every stage of our mantissa. We have 7 functional units. Their performance, hence, depends on the precision involved during the calculation, and it depends on the operands and on the output precision configured in the register file. And as I said, some per stages work with full width in order to minimize the overall latency of our operation. We did several hardware prototypes, thanks to the EPI project in collaboration with Cyperl and Jupyter HPC. The first prototype dates 2021. It was the EPAC test chip 1.0. Here we were supporting 256 bits of mantissa precision with the Unum Type 1 memory format. This was a bad decision. And we support 2 dynamic formats in memory running at 1 GHz. Then we had the second temp out, the EPAC 1.5, and here we did a major reconstruction of the architecture. First of all, we support 512 bits instead of 256. We support the extendable memory format from the IEEE 754 standard. We support 8 dynamic data format, indexed load and stores operation with all misaligned data as packed as maximum in order to maximize the efficiency when dealing with vector. And the working frequency is still 1 GHz. Then we had an FPGA prototype in order that we can change faster the architecture and make easier experiments while waiting the chips from the tape out. And we implemented the last circuit, RIA, that should come at the end of this year, beginning of the next one, depending on the TSMC and the other partners of the project. And here we got the same properties as in the EPAC 1+5, but we got 4 parallel VRP cores in order to have a little bit of parallelism. We also provide a software stack. Why? Because people must use it and must be able to program the architecture. Normally, in scientific computing, you have to deal with solvers. One classical example is CG, which stands for conjugate gradient. Without going too much in detail, just to tell you how it works, there is the application need that can run on your data server, that sometimes you have to call the critical kernel conjugate gradient, the one that we spend 80% of the time doing computation. Now we offload this job to our architecture, where there is standard C code, up to the point that we want to call the core, the kernel, the BLAST library, we want to solve the matrix, the linear system with a large matrix. And here we provide a BLAST routine, where basically we've written down in assembly all the instructions that are scheduled in such a way to minimize the latency as much as possible, and then we run on the hardware. But we didn't stop to the hardware neither. We want to share this technology to other people. We also provide software emulations in Spike and software emulation within MPFR in order to also be able to the mathematician to explore a bit their algorithms. Moving on case studies. So why this thing is useful. Here we got two examples. The first one is a breast tomography example. It's a paper that we just submitted a few weeks ago. We are waiting the response. The thing is that we want to get a breast tomography. There are several issues in the breast tomography. The first of all is that in order to make it converge, we need a lot of ultrasound sources. More the ultrasounds, less precision you need to make it converge. But this makes the device pretty complex, and there is no guarantee to converge the algorithm. And as you can see, the algorithm doesn't converge for less than 128 bits. By increasing the precision, we get multiple advantages. First of all, we halve the number of iterations for the same number of ultrasound sources, and even more, you can get the converging algorithm for far less ultrasound sources, which makes the device, the medical device, easier and cheaper to build. Then we did a second benchmark, to solve matrices. And here we get three major takeaways. The first one is that augmenting the precision is not always open bar. We arrive in a given point where there is no more advantage of increasing precision because we already get the minimum number of iterations. And then here we can get the optimal points that change over time. We get a speed up of almost 80% in computing time. And then, moreover, we can get some matrices that don't converge with lower precision. And here, just by augmenting the precision, we do any pre-computing on the matrix, we are able to make our matrix converge. What's next? We want to work on a eigensolver to have a broader evaluation. We want to implement a C compiler, and I'm here to say that we are hiring people, so if there is someone that wants to collaborate with us with a new compiler, either for a project, either coming to work to us, you are welcome. We are ready for a tape out with 8 core with Cyperl, and we plan to have out-of-order execution and better support for sparse matrices as well. However, there are still some open questions, like what's the impact of having a higher precision generally in a result, regardless of the application? What to choose the right sweet spot, right precision during the calculation? What's the right granularity that you should have to tune our precision? These are all open questions that now we don't have yet the answer, and we are here to ask for collaboration if someone wants to work with us and try to answer this question all together. So, concluding, we proposed a hardware accelerator with a full software stack based on RISC-V. We demonstrate that having extended precision is useful and that all our results are silicon proven, so they are actually working. Here there are the publications that we get out of this paper, and I'm here to thank you for your attention. If you have any question, I'm here, or in the poster section at the post 814, if you want to talk more after. Thank you very much.
So I would invite you to then go to the poster and then put the questions because we are really at the hour. So
thank you.
Yeah, once again, thank you.